All right, welcome back. We are now in 32.6, which is fission. So fission is I think I can do this and make stuff legible. If I can type, process where nuclei are split. Oh, that's not helpful. That's helpful. This is actually something that happens that we can control here on Earth. It's nuclear energy, right? Like, I don't have the chart anymore. I can probably get it, but I'm too lazy. I don't know. But the chart we looked at the beginning of fusion, the lower mass particles, it would cost more energy to fuse those than you would get, to induce fission on those than you would get out of them. So again, anything beyond iron, when you do fission, when you break these things apart, you will get energy out of them, a net energy out of them. So we're talking about the heavier elements, and typically we are looking at things like uranium, plutonium, things like that. So we have a question just right off the bat here. Calculate the energy released in the following spontaneous fission reaction. Right. So this is a uranium that just breaks apart into strontium and xenon, and then there's 3 neutrons that are released. So we need to know some of the masses in order to do this. The mass of, and these are all in Appendix A, but I'll just write them out here. The mass of uranium-238 is 238.0507. I really should have typed these, but I can't do the 238. So anyway, 050784 U. Dude, I'm not writing these. The next one is the mass of strontium. I'm just going to write it as this. Strontium 95 is 94.919388 U. The mass of xenon, is it 140? Yep, is 139.92160 U. And the mass of a neutron is 1.008665 U. So we have those 4 values, right? And all I really need to do then is find the mass difference between the uranium, right? I need my pen, this pen. So I want to find this value. I want to find the mass of 238 uranium minus the mass of everything else. So I'm just going to call this the product. So mass of the products added together. So I didn't write it down here, but I did write the result. So you would take this value here, the mass of the uranium, you would subtract off 94.919388 U, and then subtract off 139, and then multiply this value by 3 because there's 3 neutrons, and then subtract that off. And anyway, I'm going to shortcut this because I've had to do 9 of these videos today, and I'm ready to just drink myself to death. But we end up with 0.183791 U. So they asked for the energy. We needed that because in E equals that delta M C squared, we have now the M. So that is equal to this mass, 0.183791 U. I'm going to convert it out of U by multiplying it by 931.5 mega electron volts per U per C squared. And then that gets multiplied by the C squared. So the C squareds cancel out. That's nice. And then I end up with 171.2 mega electron volts. Right? So that's a large. It's a pretty big dump of words. All the words are gone. Energy. It's a big dump of energy. So this is a spontaneous fission, but and this can happen, but it's not likely to. So uranium is typically not going to go through this reaction as we see it here just on its own. It can, but it's more likely to go through an alpha decay. So this 238 uranium is more likely to split spontaneously by means of an alpha decay. That's what we would end up seeing way more often than this spontaneous split into strontium and xenon. Why can't I delete stuff? Guys, oh my gosh, I'm so done with this program. Just want it to die. All right, well, I can't delete my program. It just hates me, and there goes my pen. What is happening here? Just go. Go away. All right, well, I'm going to dump this whiteboard. And here's a new one. No, don't do that. Don't do that. All right, here's a new whiteboard. Pen, I'm losing it. I don't even know where I'm at now. Not there. All right. There's a picture. Hey, there you go. So what more likely will happen with these larger fissions is neutron induced. So a neutron induced fission is, let me grab this. If I can grab, I'm going to have to grab this in parts. We're going to have this neutron come barreling at a nucleus. Right? And the neutron has no problem coming into contact with that nucleus because the neutron, being neutral, is not repelled by the Coulomb force. Once that thing, once the neutron gets close enough into this thing, it can be absorbed when it starts to experience the nuclear strong force. Right? So it comes and gets absorbed into that neutron. But these neutrons, now we're talking about large, heavy elements, and they kind of behave like a liquid droplet. This neutron comes and it dumps all of this energy in, and what was this, you know, if you can picture just a little raindrop, which is a spherical, not a teardroppy looking BS thing, but just a ball, a little sphere of water, and something comes and slams into it real hard, it's going to expend that energy, and it, just like the picture on the screen, it's going to kind of squeeze as these ends kind of go in opposite directions. But once we've got this big of a separation between these. This is really big, by which I mean something on the order of 10 to the negative 15, but it's several femtometers, right? And so it's big enough that the strong force doesn't interact between these two sides, and the Coulomb force does. And so now all of a sudden the Coulomb force between, say, this proton here and this proton here is large enough that it overpowers the strong force, and wait for it, you'll all be so excited. Oh my gosh, get out of my way. And these two blop, just like a water droplet. If it gets spread too much, they just break and they're out. And what happens when that happens, what we also see when this happens is typically neutrons will break free with it. And so it kind of splashes, if you will. But we get these, in this case, 1, 2, 3 neutrons bail out. Let me see if I can get this whole picture here. The good, the bad, and the ugly about this is, wait, will you not do what I want you to do? Let's say we have right here a neutron that comes and plows into a uranium-235, and it creates these two daughter elements, these two smaller things. But it also sends out 3 neutrons with a lot of energy. And those 3 neutrons can then go find another uranium, break it into 2 things, and send out more neutrons. I don't know where the third one is. It disappeared. But right, each one of these, there's 1, 2, 3 that gets sent out, and each of these sends out 2 or 3. Apparently, it gets to decide. Should usually be 3. But this is called, if there's enough of these uranium nuclei in the vicinity of these neutrons before they lose their energy or interact with something else, then we have what's called a runaway nuclear fission. So it can be dangerous if we just pack all this stuff in and flick a neutron into it. We can blow up cities. But our reactors don't. They do. Chernobyl did, and we had some disasters like the Fukushima plant in Japan. That was earthquake, induced initially. But we've had some disasters. But in the idea, why can't I copy? The idea is to be able to control it. And in these power plants, essentially what's happening is you'll have these rods in here. They're in water. Well, that's not what I wanted. Oh my gosh, stop it. They're in water. If the water stops going into the this tank, the neutrons don't get thermalized, which means they don't get the energy they need in order to continue on this process, and then it stops the reaction. Chernobyl was kind of a different thing. The water ran out, but the reactions didn't, and with that, in the absence of the water, they didn't have this safety mechanism in place, and so once the water ran out, the heat actually ran away. It increased quicker than they could control it, and they had a meltdown. And the idea is, of course, to avoid that, as if you know anything about Chernobyl, that area is basically off limits in a several 100-mile radius for, ever, basically now. The interesting thing, though, is if this does interest you in the slightest, there's some documentaries about Chernobyl. And if you don't know, it's spelled think. But animals and plants have grown, right? They've abandoned the city. Everybody had to leave. Yeah, I spelled it right. I just checked. But plants have overtaken all these buildings, and these plants are taking in this radioactive, substances, and there's wolves and foxes, and these animals are absorbing these radioactive, all this radioactivity around them, and they're still thriving, and they're still doing well, and they're wondering why. There's even families that live in the exclusion zone. They refuse to leave, and they've just been living there. Several, a large portion of them died of cancer, but the ones that didn't are now kind of a medical wonder, and I think they're going to probably start trying to see if there's some sort of DNA resistance to these radioactive effects. But that's neither here nor there, and I also now don't know what I was talking about. So there's a couple of terms that we would want to know here. The critical mass is, I'm going to type this because I just can't with this writing anymore. The minimum amount of mass of material, yoink, necessary for self-sustained fission. And then we would also have, that's helpful, thanks. This program drives me nuts. Yoink. And then we'd also have, I can't type in my field that I just wanted to type in. I just want to write something. So obnoxious. And we would also have criticality, which is the what we call a self-sustained fission reaction. And we have super, spelled with now a C, super criticality. And that is an exponential increase in reactions. So clearly, this last part we would love to avoid. We haven't always avoided it, and it's been disastrous. But we can do that with these controls in place. Hopefully, we can maintain that. But these nuclear reactors that we have, the U.S. has several of them. China is throwing them up like, a kid with a Lego free pass. I think China's throwing them up at a rate of 1 every month was the last stat that I read. But other places are very opposed to them. Australia and New Zealand don't have any at all. A lot of people have sworn off of nuclear energy, but as the global warming crisis becomes more and more of an issue, we need to move away from burning fossil fuels. We need to move away from chucking carbon dioxide back up into the air anymore. And so nuclear energy is kind of taking a swing back. And the idea now is to not make them so huge that when something goes wrong, Chernobyl happens. So they're looking into making smaller ones that might, power a city rather than half the country, and distributing them. Let's take a look at a problem. calculate the energy from a kilogram of fissionable fuel. So I'm going to calculate the energy produced by the fission of 1 kilogram of uranium-235, and they give us that the average fission reaction of 1 molecule of uranium-235 produces 200 mega electron volts. So first, note that 1 mole of uranium-235 is 235.04 grams. That's a 0, I promise. So a kilogram, which is 1,000 grams of this uranium, divided by its molecular mass here of 235.04 grams per mole, gives us 4.25 moles. Of uranium-235. So the energy is going to be 2.56 times 10 to the 24 Oh, sorry, I skipped a spot. That's what I get for reading. Back it up. My bad. So there's one more thing. I was like, I don't know where I was going with that. So if I take this 4.25 moles of 235 uranium-235, and I multiply it by Avogadro 6.02 times 10 to the 23 molecules of uranium-235 per mole, I get this number, 2.56 times 10 to the 24 235 uranium atoms. You don't typically write your atoms if you just have the element, you know that you have atoms. But then the energy is that many atoms, 2.56 times 10 to the 24 of these guys, 235 U's. And I'm going to take that and multiply it by this. There's 200 mega electron volts per atom. So 200 mega electron volts per uranium-235. And then I'm going to convert that out of mega electron volts with 1.60 times 10 to the 13 joules per mega electron volt. And in the end here we've got 8.21 times 10 to the 13. 13, that's a 13, I promise. 13 joules, right? Which is pretty big amount of energy. We're talking about 1 kilogram of uranium. We process it through a nuclear plant, we get that much energy out of it. This is approximately what we would get out of 600,000 gallons of gasoline. So it's pretty good numbers. The energy per kilogram of actual fission fuel ends up being less because there's far fewer moles per kilogram of the heavy nuclides. Fission fuel is also much more scarce than fusion fuel. None of that matters. Anyway, we get quite a bit of energy out of that, but again, we, especially Americans, love our diesel trucks and our gas guzzlers and things like that. So it's hard to be able to walk away from stuff like that. But we probably will, or we'll all die. I don't know. But anyway, that's it. The next section was nuclear weapons. I think I'm not going to do a video because I've looked over the section and it looks like a nightmare to try to do a video of this. It's not going to translate very well. It's 32.7. Read through it if you like, but I think I might just end up dropping it from our list of sections to worry about. It is interesting, though. If you like, read through it. It's interesting to see how we've weaponized just about everything in humans' history, and including this. But this is quite the weapon. So anyway, thank you, and enjoy your Thanksgiving weekend, and I'll see you guys on Monday.